As we look at section 7.1 entitled Roots and Radical Expressions, we're going to review a little bit more about the property of square roots and then expand that to the property of cubed roots, fourth roots, and so on up the ladder. Just as a review, remembering that the square root of two numbers can be written as the product of the square root of one number times the other number. And yesterday we talked about breaking up a square root into a perfect square and then what was left over. And so let's just review that idea a little bit here down in the first section. For example, in the square root of 128. The perfect squares, as a review, are 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 25, 36, 49, 64, 81, and 100. So a perfect square that goes into 128, I hope you realize, is 64, and what is left over is 2. So the square root of 64 comes out as 8, and then the leftover is the square root of 2. As we look at 450, the perfect square that goes into 450 of these numbers, perhaps you might try to figure that out. You might want to realize those square roots are 25 times what is left over. And so very simply, how many times does 25 go into 450? Well, you could take out your calculator and divide 450 by 25, and you would see it goes in 18 times. So 18 times 25 is the square root of 450. So that comes out as 5 square root of 18. Now you might realize that the square root of 18 is still able to be broken down further. And so we would break down 18 into 9 and 2. That would give us 5 times 3 on the outside with the square root of 2 on the inside, or a final answer of the square root of 2. All that to be said, maybe you might have realized that the square root of 450 also could have been written as the square root of 225 times 2. If you had seen that, you would have very quickly realized that was 15 square roots of 2. So here you can see it breaking it down slower or breaking it down very quickly if you can identify those perfect square roots in a very quick manner. Let's look at C. We have the square root of 300 with the negative 5 just being drug along on the outside. Well, I hope you quickly would realize that that's 100 times 3, so that's negative 5 times 10 times the square root of 3, and my answer is negative 50 square roots of 3. Now, let's take these same ideas and apply them to cubed roots. With a cubed root, we have to think about what are the perfect cubes that are going to go into different numbers. And down here, I'm going to write out the perfect cubes as we reviewed yesterday. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and 6 cubed is 216. And so as we look at 27, we can very quickly identify the fact that 27 is a perfect cube, and so the cubed root of 27 is 3, and so my answer is merely going to be negative 12. For the cubed root of 16, we're going to break that down into a perfect cube, 8 times what's left over, 2. The cubed root of 8 is 2, and what's left over is the cubed root of 2. It is very important that you notate and put this little cubed root symbol in our answer because it is different than a square root. On F, we have the cubed root of 128. Well, the cubed root of 128, perhaps you would go over here and you'd realize, oh, 64 is 128 times 2. So that's the cubed root of 64 times the cubed root of 2, giving you an answer of 4 times the cubed root of 2. Let's go on to our next page. Little review of what our terms are. The radicand, once again, is the letter or number that's inside the radical sign. The smallest number down in that square root, as we've traditionally talked about it, is called the index or the root. So you might often hear of that also called the root. and then obviously you have the radical sign. So let's take a look at some square roots in terms of variables. We're going to remind us that we're going to make it into a perfect square times what is left over. So the first part is going to be a perfect square, and the second radical is going to be what is left over. So this being said, the square root of a to the 7th is the largest square inside a to the 7th, which is 1 less times the leftover a, gives us an answer of a cubed times the square root of a. Remember, we divide that exponent by 2 because this is a square root. And I don't know if you could realize that, but there's actually an invisible 2 in that radical sign. Let's come over here and look at the 45 a to the 5th. 45 breaks down into 9 left over 5. A to the 5th breaks down into a to the 4th, the even number directly below a to the 5th, and 1 left over a. So the square root of 9 is 3. We cut the a to the 4th in half and get 2, and we have a leftover 5a as my leftover root. Let's keep practicing with squares. 60, a to the 7th, b to the 10th. A perfect square that goes into 60. Well, if we go back to our perfect squares from before, do any of these go into 60? 49 certainly doesn't. 36 certainly doesn't. 25 doesn't. 16 doesn't. 9 doesn't, but 4 does. So 4 times 15 is 60. A to the 6th is the even number below a to the 7th, with 1 left over a, and b to the 10th is actually a perfect square because it's an even number. So we take out the 4, becomes a 2. We divide 6 and 10 by 2 and get b to the 5th and a to the 3rd, with the leftover 15 root a. Now let's apply these same square roots to our perfect cubes. Now we're going to be breaking it into a perfect cube, something times itself 3 times, or an exponent multiple of 3, once again times what is left over. How does that look to us? Well, 8 is a perfect cube. So the perfect cube, that would be 2, and x to the 9th divides evenly by 3, so that's x to the 3rd as my answer. You say to yourself, what if it doesn't divide evenly? Well, that's a pretty honest, good question. So we're going to break it into that perfect cube and what's left over. Thankfully, 64, as you know now, is 3 cubed, but x to the 8th does not divide evenly by 3. But x to the 6th is the multiple of 3 below 8, leaving us a leftover 2. Now, once again, I need to remember to put that little small 3 there, which stands for a cubed root. Let's finish this problem up. The cubed root of 64 is 4. We cut x to the 6th, not in half this time, but in thirds. So 6 divided by 3 is x squared, times the cubed root of x squared is our answer. Let's move to a little bit more complicated problem once again and look at a power of 4. Remember, on a side note, that a square root is the same thing as an exponent of 1/2. Well, a fourth root is the same thing as an exponent of 1/4. And so we have to say, can we divide 12, our x to the 12th, by 4? Well, we can. So we could write this as 12 raised to the 1/4. Well, that's simple. 12 times 1/4 is 3. So the fourth root of x to the 12th is x to the 3rd. Let's keep going and talk about real number roots. A real number root obviously is a real number that you could put on the number line. It's not imaginary, it's not complex, and so we are going backwards a little bit in terms of our real number roots. So the square root of 121, as you know, is 11. Not positive and negative 11, but just 11, because this is called the principal square root. The square root of negative 49 has no real solution. I know that there is an answer to that, but there's no real solution to our problem, because the square root of negative 49 is a complex number that you now know to be 7i. But for our cases, if they ask you for real number roots, you're going to answer no real solution. The cubed root of 27, well, 3 times 3 times 3 is 27, so that's 3. And the cubed root of negative 27, well, negative 27 is negative 3 cubed. And we're taking the cubed root of that. So we have negative 3 to the third raised to the 1/3. Well, 3 times 1/3, if we multiply these two exponents, that's going to give you a value of 1, which gives you an answer of negative 3. 0.008 is really thought of 0.2 to the third. So you have 0.2 to the third raised to the 1/3. Once again, 3 times 1/3 is 1. So the cubed root of something cubed is what's inside, or in this case, 0.2. A fourth root is kind of fun in terms of thinking about it very uniquely, because a fourth root is either the fourth root of something to a power, or sometimes you can think of it as the square root of another square root. So 81 is really 3 to the fourth. And we take that raised to the 1/4. The fourth root of something to the fourth is the number inside. But sometimes when you think about a fourth power, you can think of that as the square root of a square root. Well, the square root of 81 is 9, and the square root of 9 is 3. So either way you want to approach that is fine. How do we take the fourth root of a negative number? Well, once again, that's going to give you no real solution, because you cannot take the even root of a negative number. Okay? So we're going to write that down. Anytime that we have an even root of a negative number, you are going to have no real solution. However, on our last one here, we have an odd root of a negative number, and negative 0.2 cubed is 0.008. Well, that's all being raised to the 1/3, and once again, 1/3 times 3 is 1, and so negative 0.2 is my answer here. I hope you see now that after working with some examples, when can you have a negative answer when working with radicals? Hopefully you realize the answer when the root is odd. All right, and that concludes our lesson for today. I hope this has been helpful in explaining this to you. Remember, often it's going to be helpful to rewrite sometimes our roots as fractions and multiply those fractions times our exponent, and then when those cancel each other out, what's left is what is inside that original radicand.